Okay, class, welcome to the next lecture. Today I'm trying a different angle, so we'll see how that goes. Okay, so today we are learning about set theory, and it's the intro to it, the first lecture on it. So the idea is that so far, what we've done is sort of learn how to prove things. So we've seen proofs, but really everything has just been about numbers and like things you sort of already have seen before. Maybe you didn't know they were true or not, but sort of boring proofs, I would say. And that was like the playground with which we would learn how to prove things because you already know about it. So next, we're going to learn a new subject. So the idea is it's a better way to organically practice proofs because proving stuff that you don't know already is true and you're unfamiliar with. Okay, so this new subject is called set theory. It'll have facts that you don't already know that will prove. And the first thing to start the lecture of what set theory is we need to figure out what the heck a set is. That's what it's all about. So I'm going to define a set. Set is a collection of elements. So don't think too much about it right now. I'll give you lots of examples. So which we write inside of these fancy curly brackets that only PhDs can draw. And so that's what a set is. So in math, you'll discover that trying to define something is hard. If you want to define everything, you can't do that. So a set is a collection. It just sounds like the same thing. It's just another word for set. But it's really just a list of stuff. And the stuff inside the set is they're called elements because they're extra fancy. So it's just way easier to understand what sets are with examples than it is to just say what a set is. So it's a collection of stuff inside of these brackets that I list. So I'll just list some stuff. A, comma, X, comma, the number 2, comma, the word chair. So this is an example of a set. And what we can say about it right now is not much, but we can say it has 4 elements because it's a list of 4 things. So like, what are the elements? A is an element of this set. X is another one. But like the number 25 is not, because it's not in the list. So I should be saying of the set, but I don't want to write so much. Okay. So 2 is in the set, chair is in the set also. Okay, so that's what a set is. And then, because we don't want to write so much, what we do is we name sets. So you can name sets too. This will save lots of time later. So for example, I could just say that A, usually we use a capital letter for the name of a set. I could say A equals, and then I could write down a set. I don't know, 3, 5, 2. And B equals the set with just one thing in it, the word apple. So those are 2 other sets that I've named. And so that way I can call back to them later when I have more notation. And yeah, so now we just need more notation to do that. Okay, so we can use the notation. It's an epsilon, I guess, I think it is. But it looks like that. And what it means is an element of. So then putting this fancy notation together with what sets are, we can say things like that, like this. So you'll see this a lot. So for example, the number 3 is in the list that defines the set A. So I could say that 3 is an element of A, and that makes sense to write. And I could say 5 is an A, and I could say 2 is an A. But what's not an A is like the number 10. So I could say something like this: 10 is not in A by crossing it out. And I have another set B, so I could say like apple is in B, but 5 is not in B. So you can write things like this. This is how you use the notation. There's just a faster way to say that, yes, this thing is in that set or it's not. That's all it's doing right now. So then a very little subtle thing that people mess up on is something like this. So what if I just have a set with the number 5 in it? So it's just a set with one thing in it, one thing in the list, just number 5. Then I can write something like this. I could say 5 is in that set. So that makes sense to write. But I can't say this: 5 is in 5. An element, elements are always in sets. So when I say something like this, it doesn't make sense because I'm saying an element is inside of an element. I have to always be in a set if I'm an element. Okay, so just be aware of that. It's a very common mistake. One more little subtlety is that order doesn't matter in sets. So you could say something like the set with 1, 5 in it, or you could say the set with 5, 1, and they're the same. And then also repeats don't count twice or multiple times. So if I say the set with 8, 8, and 8 in it, that's just the set with 8 in it. Okay. All right, so what else do we need? Well, we're just getting familiar with the notation, so we're just going to keep doing more of that. I guess the next thing is that what happens if you have like a really big set? So for big sets with lots of stuff in it, you might write something like this. So say I wanted to list all the numbers from 1 to 100. Well, I'm not going to actually list them, but it's going to be implied what's in there. If I write it that way, that's going to mean all the numbers from 1 to 100, all the whole numbers from 1 to 100. So the elements are sort of implied without having to actually write them all down, because that would be too long. Let me name this set so I can call back to it. So for example, like 50 is an S, even though I didn't write 50 in there. But it stops at 100, so 101 is definitely not an S. And fractional numbers are not implied because I'm listing whole numbers. So like 5.32 is also not an S, even though I didn't indicate precisely what was an S and what was not. Okay, so it's all implied, but that's just to save time. All right, so next, what about this? We can even have infinite sets. So that means that instead of 100 things, it has infinitely many things. So how can I indicate that? Well, I can just use ellipses, and I can just not stop. So before I end it at 100, but here I won't, and that just means that I'm including all the numbers, 1, 2, 3, 4, and so on forever. Or I can go in both directions if I want to indicate in the negative direction, I could do something like this. So that would indicate the set with all the whole numbers in both directions. AKA this would be the integers. We'll talk about that later. Actually, we'll talk about that now. Okay, so some sets are so important that they get permanent names because we have to reference them so many times. And here is the first one. So they're supposed to be boldface letters. So this is supposed to be like a boldface N. I'm not very good at drawing it despite my PhD, so sorry. But this set is the set with the whole numbers starting at 0. So 0, 1, 2, 3, and so on forever. And it has a name. It's called the set of natural numbers. And yes, it does include 0. 0 is perfectly natural. If someone ever tells you 0 is not in the natural numbers, then I'll have something to say to them because they're wrong. So yes, N, boldface N is the natural numbers. It includes 0. Okay. The next one, you would think it would be an I because it stands for the integers. So I'll just list them out before I reveal the name. So it's all the whole numbers, positive and negative and 0. And it's called the set of integers. But it should really be called the set of zintegers because it's a boldface Z. I don't know why. Probably, I think the Germans did something to make it be a Z. I don't know. Let me draw it better though. It looks like crap. Okay, so the zintegers are all the whole numbers that are positive and negative. And there's more, but we'll get to them in a second. But first, we have to realize that actually some sets are really hard to describe through listing. So we need a better notation. So some sets are hard to list out elements for. And in fact, some sets you cannot list all out. You cannot list all the elements, but they still are sets. So we need another notation, and it's called set builder notation. I guess because you build the set out of smaller pieces. I don't know. But here's how it works. You still use these curly brackets, but instead of listing everything out, you just like be a little bit smarter than that. So what you do is you say, I'm gonna say the type of things in the set. So am I talking about numbers? Am I talking about people? What am I talking about? Letters, words, I don't know. Types of things in the set. And then you draw a vertical line that really just means such that. And then the property that defines the things in the set. So you could think of it as like the properties obeyed by elements in the set. So instead of listing out all the elements, what you do is you write the properties that they obey, and that tells you the elements because you're supposed to know what things obey these properties. So as usual, it's just way easier to see with an example. So we'll just jump right into it. So I could write something like this. X, so what type of thing will X be? It will be an integer. So what I'm saying is the things in this set are first and foremost integers. But I'm not just going to leave it at that because then I would just be saying the integers again. So it'd be weird to write it. So I'm going to say like what kinds of integers? I don't want all the integers. So the integers that do what? The integers such that what happens? Well, how about the ones that are equal to 2 times something for some y in Z. So here I'm saying not all the integers, just some of them. So which integers? Just the ones that look like 2 times y for some y. This one can be listed out. This is actually the same as, see if you can figure out what it is. I'm just saying the even integers in a fancy way, because the numbers that can be written as 2 times something else for some other integer, those are just even numbers. So I could list it out as well. So AKA the even integers. That's what this set really is. I just described it instead of listing it. Okay, so a very important skill that will come up a lot is to be able to say what it means for something to be in a set. So let's call this set S. It doesn't have a fancy name, even though it's just the even numbers. So something that you should be able to do is you should be able to say, if I have something in the set, what can I say about it? It means that it obeys, first of all, this. It is one of these things. And second of all, it makes this property, which is actually a predicate, be true. Okay, sorry, it's crappy. Oops. So it just fulfills this property. Let me just circle the whole thing. Okay, so in this situation, that would mean that a is an integer and a equals 2y for some integer y. And in general, you'll often have a set that looks like x is in something, some other previously defined set. So I guess I can just use some other letter like a. So let me change my eraser back to the other kind. Okay. Such that, and then a predicate involving x. That's really what set builder notation is about. So then if you say, I'll use a different letter, b is an S, that's going to mean that b is an A and P of B, it makes the predicate be true. So this is going to come in handy later, so just don't worry too much about it right now. But then in the opposite situation, what does it mean to not be in the set? That's something we should also think about. So when we're just listing stuff out, it's sort of easier to see, like, okay, what does it mean to not be in here? It means it's not an even number, so it's not in this list. But then when we think in terms of properties, what does it mean to not be in here? Well, it could mean that it's, first of all, not an integer. So that would be one reason to not be in here. But it could be an integer, but then not obey the property. So there's a couple ways to think about it. So if A is not in S, what that really means is that it makes P of X false. So the negation is true. I guess I should specifically say when I'm plugging in A to the predicate. Okay, so that'll come back later. It's a little bit abstract right now, so I don't want to get bogged down too much by it. I guess in this situation, I could do that one more thing. So like, if A is not in here, that means A will not equal 2 times Y. So the negation of A equaling 2Y is the true thing. This is false and this is true. Okay, so it's very connected to the logic stuff that we've done before. All right, we'll bring that back up when I need it more. Okay, so let's do more simpler examples for now. Okay, so here's another set I could describe with set builder notation. So I could say x is a natural number such that x squared minus 4 equals 0. So what's this set? Well, the things in here have to be natural numbers. So they must be in this set, which starts at 0 and just goes up forever. And they must make this thing be a true statement. So if you just solve it, that's not enough because, oops, you'll get x equals plus or minus 2. But although both of these numbers fulfill the property, they're not both in here. So in fact, this set is just the set consisting of the element 2. Negative 2 is not in there because although it fulfills the property, the predicate, it makes the predicate true, it's not, negative 2 is not a natural number, just 2 is. Okay. Meanwhile, if I change the n to a z, now I'm allowed to include both solutions. So this set is the same as that set, but listed out instead of in set builder notation. Okay. So then just one more little remark. So I know it's a lot of notation all at once, but sometimes we actually are a little lazy with the notation. So we are less careful and we write things like this. So sometimes you don't say what kind of thing X is over there. Instead, you say it in the property side, the predicate side. And that's okay too. It's just not as perfect, I guess. Okay, so now that we have this set builder notation, we can describe the next permanently named set. Because it's really hard, although it is possible to list out everything in this set. It's called Q. I don't know why it's called Q. And it's the set of rational numbers, which we have talked about, but we haven't said the set of them. So it's numbers of the form a over b, where a and b are both integers. So it has to be able to be written as an integer over another integer, and b cannot be 0. So this is the set of rational numbers. So lots and lots of numbers are in here, like 1/2, 1/3, 10/7, negative 10/7, all those types of fractions. And there are also lots of numbers not in there. So numbers not in Q are called irrational numbers. And numbers that are like that are like pi cannot be written as a fraction of 2 integers. Neither can e or square root of 2, which we've proven before that one. So lots of numbers like that are irrational numbers. So then the next permanently named set is called the real numbers. And it's the set of rational and irrational numbers together. This is where the word and comes back to haunt me. So I don't mean and in the math sense. I mean and in the sense of putting both together. So the set of rational numbers and the irrational numbers all together. And this is called the set of real numbers. Now, you might ask why I haven't tried to describe it using set builder notation, and that's because that's for a whole nother class. That's much harder to do than for rational numbers. So I'm going to leave that to another class. But what you should do is you should think about the set of real numbers as just being the set of all the numbers except imaginary numbers. That's what's missing. And we're not going to use those very much, so I'm not going to talk about them. Okay. The point is that this one is hard to write as a set, so we're just going to leave it like that. Okay, so now using all this notation, we can do lots more stuff faster that we've done before. So using set notation, you can write previous statements quickly, which doesn't necessarily help you understand them, but it is nice. So for example, if I first define a set S to be the one that I talked about earlier, the even numbers, which can be written like this. So again, these are the even numbers. Then I can write a statement very quickly. I can say something like this that we've seen before. For any X in S, I can use a different letter. I don't have to use X again. S is already defined to be the set, so I have to use that. But X can be a different letter. For any X in S, X squared is greater than or equal to 0. Oh, wait, sorry, that's not the one I want to do. I'm mixing up my two examples. For any even number, if you square it, it's still even. So that means it's still in this set. So a very quick way of saying for any even number X, X squared is an even number. So it's good to be able to read statements like this and understand them. Okay, so we're just going to keep going through lots of examples of sets that get slightly more complicated as we go. So here is another example. I'm going to use different letters because you don't have to always use S. So what about this set? Let's think about this. So it's going to be the real numbers such that, so it's not all the real numbers, just the ones whose square is less than 4. So what we want to do is we want to be able to think about this set maybe like visually or try to understand it better than when it's just described like this. So if you're saying that X squared is less than 4, what you're really saying is that the square root of X is between, sorry, not the square root of X, but if I square root both sides, I'm really saying that this, but I'm forgetting about the negatives. So I'm really saying this. So X squared being less than 4 is really saying that X is between negative 2 and 2. So you can describe the same set with seemingly different properties, but it's actually the same. So I could have written it exactly like that instead. So this is just all the numbers between negative 2 and 2, not including negative 2 or 2. And then you can visualize these on a number line if you really want to. Maybe it'll help. And so people draw like an open circle on the 2's and the negative 2's because they don't include them. So it's all it's like the filling in between negative 2 and 2, all those numbers. So then when you say that something is inside of the set, you should be able to say what that means. So if you have an element of the set, what can you say about it? You can say the property. And then you can say, well, actually, that means that it's between negative 2 and 2. Okay, so, okay, so what else? So then we should also think about what happens if you have something that's not in the set. Let's use this specific example. So if something is not in the set, that means it does not fulfill the property. So then it's not the case that b squared is less than 4. But saying it's not the case that something happened is just negating it. So that just means that the negation of this thing is true. Well, what's the negation of something being less than something? That it's greater than or equal to it. So for something to not be in the set, I can just negate this, and that'll be what it means to not be in the set. So that's a nice little thing we can do. People also write stuff like x comma y at the same time. So you don't have to say them separately. That just means let x and y be an a. So then you can say like x squared is less than 4 and y squared is less than 4. So you'll see lots of things like that in the future. Trying to cover all the little things. What else? Okay, let's just think about another set actually. Okay, so a new set. I'll use another capital letter, x. So let x be. So this time I'm going to write it a little bit differently, because again, the set builder notation is not always set in stone. I can write the property on the left if I really want to. So I can write something like this. So this set is going to consist of things that look like 3n plus 1. And then I'm just going to say what kinds of things n is. So n will be a natural number. So what is this set really? Well, this one I can list out. The previous one I couldn't really list all the numbers between -2 and 2, but I could visualize it as like on a number line. Here I can't really visualize it, but I can just list it out. So the natural numbers are the numbers starting at 0 and up. So if I just plug in 0, that'll get me one element in the set. And then if I plug in 1, that'll get me another, and so on. So this set consists of 1, 4, 7, 10, and something like that. So the pattern is you just add 3 to get to the next one, and that's what this set really is. And again, I could have written it using better notation, which is to say I could write something like this. I could say it's going to be integers. Sorry, not integers. Well, I could keep it as integers actually. It's going to be integers such that, well, I don't want all of them. I just want the ones that look like 3n plus 1 for some n in the natural numbers. And that's describing the same thing. And in fact, I could change this to real numbers because it's not going to actually add any more. It's going to be the same set. And that's because this property is still defining the numbers that are in the set. So any of these actually result in the same thing. So just because I use R, real numbers, or just because I use Z, doesn't mean that the set has all of those in it, right? That's the point of the property, is to cut those down to only the ones I care about. And the only ones I care about happen to be natural numbers, which means I could have just started by cutting down to natural numbers in the first place. but I didn't need to. Okay, so then what comes up a lot is people write things like, again, I'm going to do this. So then if I said like, let A be in this set, which I called X a long time ago, then you want to be able to say what that means. That just means that A equals 3n plus 1 for some n in the natural numbers. And I could have said that way up here, even though I wrote it in sort of a much quicker way. I didn't say X equals there, but that is still telling me what elements look like. So if I have an element in here, I can just say it looks like 3n plus 1 without needing to explicitly use an equation in the property. Okay, what else? Let's see some more examples. Lots and lots of examples. So if I said let X be in the set of real numbers that are bigger than 5, that just means that X is a real number and X is bigger than 5. And if I said that Y is not in there, whoops, it's the same set, so I'm not going to change those letters. If I said that Y is not in there, then that's going to mean, well, Y could still be a real number. What it means is that it's not going to obey the property. So Y makes the negation of the property be true, which means that Y is less than or equal to 5. That's the negation of Y being bigger than 5. Okay, so that's what you would know about it just by it not being in the set. Okay, so this is all mostly notational stuff. I'm trying to get used to the notation and understanding how to put it all together. So next, what we want to do is think about what we can do with sets. So generally, when you learn about a new topic in math, the types of things you do are you say like, when are two the same? And the same can mean many different things. So we're going to leave that very vague. We're not going to answer that question. Not yet, at least. When are two sets the same? Can I combine sets in different ways? Or can I put them together? Sort of like when you learn about numbers, then you learn about how to put numbers together to make new numbers in different ways. And then always like properties of sets. And that usually goes hand in hand with the ways in which you can put sets together. So that's what we're going to do first, is think about how I can sort of combine sets together. So this is the first big definition. Given two sets, A and B, I want to think of them sort of as like numbers that I can glue together. So what can I do with two sets? Well, I can think about what they have in common, and I can think of that as a way of putting them together. So that's called the intersection. So the intersection of A and B, which we write using this notation, written as A, this is called a cap, B, but you read it as A intersect B, is the set of elements that are in both, that are in common to both sets. So they're in both A and B. So then, to be super precise, I'm going to write this in a very mathy way. So A intersect B is the set of, well, let's just think about what this is saying, the set of elements in both A and B. So it's the set of things, and what do I know about those things, those elements? I know that they're in A and they're in B. And that and is the mathy and. So in fact, if I really wanted to, I can think of it as two predicates that I'm anding together. And that comes in handy when I do negations and I think of what does it mean for an element to not be in here. If I use logic, logical notation, I can maybe think about it a little bit easier. So before we do that, we'll do an example just because it's easier to see what's going on. So if x equals 1, 3, 5 chair, y equals 2, 3, 5 apple, and z equals 2, 4, 5, then I can combine these sets using intersection. So for example, A intersect Y is what? Well, what do X intersect Y? What do X and Y have in common? They have 2, 3, and, nope, they don't have 2 in common. Sorry, they have 3 in common and 5 in common. And that's it. If I do X intersect Z, then they only have 5 in common, right? And I can intersect more than 2 things at the same time. And again, the only thing in common to all 3 would be 5. So just be the set of consisting of the element 5. I could do one more. So like if I do Y intersect Z, then they both have 2 and 5 together. Okay, so that's how intersection works. And it is very much like the word and was in logic. And we'll see later, like the properties are very similar that they obey. But for now, I do want to think about this again, which is to think about what happens when you have something in the intersection of 2 sets. What can you say? Well, then you get to say that A is in A and A is in B because it obeys the property, and the property is that it's in A and B. And if you just change the set letters to X and Y, or happy face and sad face, it would work the same. So if X was not in, I'll use different letters, C intersect D. What the heck, did I just erase something? Where'd that go? You know, A is an A. Did I just say it and not write it? Oops, okay. So you know that. So if you have something that's not in the intersection, then what is going on? What the heck is going on with my iPad? Okay. All right, disappeared. So, okay, one more time. This video is long enough without these interruptions. Okay, so now if I know something is not in an intersection, so these different letters just for practice, then what can you say? Well, then you can say that it's not the case that X is in C and X is in D, but when you negate an and statement, you negate each piece. This is De Morgan's law, and you change it into or. So when you say that something is not in the intersection, what you're saying is it's either not in C or it's not in D. Okay. So just something to think about. All right, so the next definition is sort of like the opposite of intersection. Given two sets, A and B, the union of A and B, which is written with a cup A, cup B, but read as A union B, is the set of elements in either A or B. So just everything you could possibly imagine that comes from A or B. So then using very fancy math notation, meaning the actual word or, you can write it like we did for intersection. So it's the elements that are in A or in B. And it really is that or, the logical or. So to be in the union in A union B means it just has to be in one or the other. It doesn't have to be in both, but it's got to be in one. It could be in both. Okay, because that's what or means. Or means either statement is true. So X could be in A or X could be in B. As long as either one is true, then it's true. So then just like before, if A is in a union, then you get to say that X is in one or the other, but you don't necessarily know which one it is. But it's got to be in one, at least. Could be in both. But if you know that something is not in a union, then it's the same idea as before. That means that it's not the case that it's in A or B, meaning that using De Morgan's law, it's not in A and it's not in B. So this one's a little bit easier to understand just using plain English. If A is not in this or that, that means it's not in either one. That's what this is really saying. Except I used the letter B instead of A, but yeah. Okay, so just another example. If X equals 8 and 10, A equals 3, 5, and 10, and Z, I'm just using different letters for practice, 1, 2. Then you can write all sorts of stuff. So X union A would be 3, 5, 8, and 10. Remember, you don't count 10 twice because sets don't care about if they're in there twice or not. So it doesn't matter that 10 is in both. As long as it's in one, that's enough. And I don't double count. So X union Z would be 8, 10, 1, 2. And then, of course, I could union everything together if I really wanted to. So I can do all three at once. So I could do 8, 10, 3, 5, 1, 2. It'd be the union of all three. Okay. So that's going to be it for today. What I want you to realize is that there are similarities, which we may have time to explore. I don't really know if we will. There are similarities between, we've already seen this, P and Q versus the intersection of two sets, and P or Q versus the union of two sets. We've already seen how they're related in the fact that this one uses and in the definition. And then this one uses or in the definition. That's one way they're related, but they're also related in other ways in that they have lots of similar properties. Okay, so that's it for today. I will see you next time.